All right, so good afternoon, everybody. Happy Friday, Happy New Year, Happy 2024. Hope you all had a good Merry Christmas, Happy New Year, and have had a good couple of weeks during the break. Yeah, so please type your name into the chat so that we have your record for attendance. I'm going to write that. Please type your name into the chat so I have your attendance record. Okay, so everybody can go type their name when they get on. Yeah, so I hope everybody had a really good 2 weeks. I'm looking forward to getting started. I'll mention this again at the end of class, but we're also not going to meet next week because I'm going to be at a conference. But I'll send a reminder about that. Oh, it seems like somebody on the chat wants the link, so let me just put the link into the WhatsApp. So baruch.zoom.us/j/88202208889. Okay. Okay, great. Okay, so welcome everybody. So let's get started. So if you remember last time we were talking about quadrilaterals, and so we had a bunch of homework questions actually that I do want to go over because I think it's going to be worth spending a little bit of time thinking about them. And then after we go over them, then today we're going to talk about just regular polygons in general, not necessarily with 3 sides or with 4 sides, but with any number of sides. And that's going to finish our unit on polygons. And then next time we're going to start talking about circles. Okay, and then that'll finish up the geometry unit. Okay, so let's start off with this first homework problem that we had last time, which was that a diagonal of a rhombus has length 16 and each side of the rhombus has length 17. And we want to find the length of the other diagonal. So I drew a picture of this last time. We had a rhombus that looked like this, and so each side had length 17, so we can just draw 17s everywhere. Remember that a rhombus is a quadrilateral with all 4 sides equal, but not necessarily all 4 angles equal. And we had one of the diagonals over here has length 16. And the hint was that there's another diagonal over here. And the goal is that we want to find the length of the other diagonal. And one thing that we mentioned last time is that the diagonals of a rhombus always meet at a right angle, right? So we're going to have a right angle where these 2 diagonals cross each other, which means we're going to have right-angled triangles in the question, and that means that we're going to be able to use the Pythagorean theorem. Isaac, do you have a question? I see your hand raised. No? Okay. All right. So does anybody want to try? Let me just draw this line a little bit better. Let me draw this line a little better. Let me draw this line just so that it's a little straighter. Draw this red line right here, right down there, and that's 16. And then we've got this other diagonal over here. So if we want to find the length of the other diagonal, what's something that we can do? Anybody have an idea how to attack this? So in one hint that I'll do, so maybe I'll label the diagram a little bit better, is that since these diagonals cut each other in half, they bisect each other, that means that each part of this diagonal is 8, right? It's 16 and it's divided into 2 segments. So the top segment over here is 8, and the bottom segment over here is also 8, right? So we want to find how long the full diagonal is. So maybe we want to start by finding how long this part of the diagonal is, and that's going to be half the length of the entire one, right? So how would we find this length over here of, say, half the diagonal?
Yeah, Dan.
Mm-hmm. Yeah, Ed.
If we look at just one segment of the diagonal, where we have the hypotenuse to be 17,
Mm-hmm.
we want to find the other half. We have to find half first. Then the half plus the other half will give us the full length of that
Mm-hmm.
diagonal. So we're going to take 17 squared
Mm-hmm.
minus 8 squared will be equal
Right.
to the value.
The squared of the value, right?
Yes,
Yeah, so that's
that's the
exactly right.
Pythagorean
So if
theorem.
I label this here with x, so if I let x equal 1/2 the other diagonal, then as Ed says, the Pythagorean theorem gives us that 17 squared is going to be 8 squared plus x squared, because those are the other two sides. Gabriel, yes, I think I did. I may have forgotten to respond. I'm sorry about that, but oh yes. Oh wait, I do see this. It came from a number. Okay, so I'm going to look at these things, but most things look right, Gabriel. But let's go. We'll go problem by problem and see how it works. But I think most things look correct. Yes, most things here do look correct, or almost correct. Yeah, no, correct. Yeah, everything's correct. Okay. Yeah, so Pythagoras' theorem is exactly right. So we have 17 squared equals 8 squared plus x squared. So Ed, do you want to continue? All right, well, so in this case, we're just solving an algebraic equation. So 17 squared minus 8 squared equals x squared. And that's 289 minus 64 equals x squared. And that gives us 225 equals x squared, which gives us that x is equal to 15. All right. Oh, sorry, Ed. It looks like you got disconnected. So we just went and solved the equation. So we get that x is equal to 15. And if x is equal to 15, what is the answer to the question? So if x is equal to 15, what's the length of the diagonal here? Right, this x here is 1/2 the length of the diagonal, right? So if that's equal to 15, then the entire diagonal is 2 times x, right? So this entire
Yeah,
diagonal.
so can we
Yep.
say, yes, sir.
Prince,
Yeah,
yep.
can we say 10?
Yep, exactly. So it has length 2x, which is equal to 2 times 15, which is equal to 30. Exactly right. So that is the length of the diagonal. It's going to be 30. Okay. So any questions on this exercise? It's a pretty straightforward Pythagorean theorem exercise. You just have to have the diagram drawn correctly and realize that you have this right angle, and so you can find this x over here. You can use that x and solve for the x using Pythagorean theorem. Okay, any questions about this? Can I use units? You could, but I mean, you don't need to. I mean, I didn't give any units, right? I mean, I could have called this 16 feet or 16 inches or 16 centimeters, and that's fine. And then the answer would be 30 centimeters or 30 inches. Usually when we do these plane geometry problems, there's often not a unit included with the problem. But you can make the unit. I mean, if I added a unit, it would all be the same. It wouldn't make a difference. Okay. Okay, so let's go to the next problem then. So the diagonal of a rectangle has length 37. The length is 1 less than 3 times the width. What is its perimeter? Okay, and so we have a hint, which is let x be the width, and then set up an algebraic equation for x. Once you know x, then you know the length as well, and you can figure out the perimeter. And I mean, the other hint, which is not written here, is that whenever you have a geometry problem like this, you always want to draw a picture. Drawing a picture will always make it easier to answer the problem. So if I draw, it's a rectangle, so let me draw a rectangle, and let me put in all of the information that the problem says. So it says that the diagonal has length 37. So I'm going to draw a diagonal here. This is going to have length 37. And then it says, well, let's let x be the width. So, I mean, I don't know which is the width or the length, right? So I'm just going to call this x over here. And then it says that the length is 1 less than 3 times the width. So if this is x over here, then what should this side be equal to? In terms of x, what do we write?
Yeah, 3x minus 1.
Exactly. Thank you, Delman. Yes, so 3x minus 1, right? It's 3 times the width minus the minus 1. Great. So we have x, 3x minus 1, and 37. And we're asked to find the perimeter. And so the perimeter, right, is the sum of all 4 sides. And since this is a rectangle, that means that this side here is also x, and this side here is also 3x minus 1. Right? So now we need an equation that's going to let us solve for x. So what's the equation that we can set up for x over here?
Oh,
Yes, hello?
yes. The first thing we
Yes,
need
Ed.
to do, we have to find the value of x
Mm-hmm.
by using the Pythagorean theorem.
Exactly. So what equation do we get?
So we have 37 squared will be equal to 3x minus, in the parentheses,
Mm-hmm.
3x minus 1 all squared plus x squared.
Exactly. Very good. Okay. And so this is, I think, 1,369. So this equation's not that easy, right? So we get...
We'll have
Yeah.
9x squared.
Yeah.
9x plus 1.
So 9x squared minus...
9x squared minus 6x.
Plus 1.
6x plus 1,
Plus-
exactly.
Plus 1.
Mm-hmm.
Plus x
Right.
squared.
Plus x
Plus
squared.
x
Remember,
squared.
yeah, so let's just remember you have to have this minus 6x because you have to do 2 times the first term times the second term. Great. So that's great. So 1,369 equals, this is going to be 10x squared minus 6x plus 1. Or in other words, 0 equals 10x squared minus 6x minus 1,368. So it's not the easiest thing. Well, we can at least divide everything by 2 to simplify this. So that 0 equals 5x squared minus 3x minus 684.
Yeah, I think that.
Yeah.
Hello?
Yes, hello, Ed.
We can use the formula,
Yeah.
quadratic formula.
Yeah, so that's
To solve-
probably easier. So this will factor, but finding the factoring is probably will take a little bit of time, will be a little hard. So I like Ed's idea to use the quadratic formula instead. Yeah, so what do we get?
So we get x is equal to minus b
Yeah, so
plus or minus. X is equal to minus b or plus or minus.
Yeah, so I'll write that over
Okay.
here. I'll write the
Okay.
general formula over
Minus-
here, right? X equals minus b plus or minus square root of...
b squared minus 4ac
Mm-hmm.
or 2a.
Exactly. So in this case, we get
We
x
have
equal... Yeah,
no we have a to be 5,
right.
b to be minus 3,
Mm-hmm.
and c is minus 684.
Yep. Great. So plugging that all in, we get minus 3 plus or minus, then we have b squared, which is 9,
9,
and then minus 4ac.
4ac.
Ooh.
4 multiplied by 5.
Yeah. So 20 times 684, whatever that is. I
It'll
feel
be negative 684.
But that make it okay.
right. So we're adding it. Right. So it's minus negative 20. And then this whole thing divided by 10.
10.
Sure.
So using a calculator, so what is this? 20 times 684 plus 9 is 13,689. And then when you take the square root of that, this comes out to be 117. So that's actually nice. So I'm just going to skip some of the algebra here. Let me just finish the problem up here. So what we're going to get is that x is equal to 3 plus or minus 117 divided by 10. And that's going to tell us the negative root is extraneous because x is a length of a side. So it has to be a positive number. So we only keep the positive, right? And so x is 3 plus 117 divided by 10, which is equal to 12. Okay, so this x over here is going to be equal to 12. And that means 3x minus 1 over here is going to be equal to 35, right? 3 times 12 is 36, minus 1 is 35. So if we have 12 and 35, then what's the perimeter of the entire shape?
It would be 2L plus 2W.
Exactly. So perim is equal to 2L plus 2W. And so that's...
So how?
Yeah, Dr. Obersh? Yes, sir.
Yes, question? Yeah, Prince?
Yeah, please, before we go forward, let's just do small
Yep.
clarification right here. Where we have the x is equal to, where you place the first TD, it's going to be negative, but you put positive down there.
Right. It's positive because the quadratic formula has negative b, but b here is negative 3. So we have negative 3, and that gives us the 3. It's a good question.
The TD, because of the TD.
Exactly. Yeah.
It's
So
okay.
that's why we have b equals minus 3 over here. And so we have to negate that. And so that's why we get a plus 3 over here.
Yeah,
Yes, Princeton?
Yeah, I have a doubt where we have 0 equal 10 s squared minus 6s, but we came down, we have 5s squared minus 3s. I'm confused.
I divided this whole side by 2, and I divided this side by 2 also. But since this is a 0, dividing it by 2 doesn't do anything. So when you have something equal to 0, you can always just divide out. But I just divided out by 2 to make the numbers a little smaller.
So that means we have the even number of 10 and 6. We look for the number that can go into both. That what I do?
Exactly. So 2 is the biggest number that's going to go into all of the coefficients. So we divide out by 2 just to simplify things. You don't have to. You could do the quadratic formula directly here, but you just end up with bigger numbers.
Yeah.
You'll still get the right answer. Yeah.
Yeah, Mr. Alford.
Yes, Abraham.
The 684 under the rule there, that should be a negative 684, but it is positive.
Yeah, so I skipped a step because I don't have that much space to write here. So what it is it's minus 4AC. So what we should have is minus 4 times 5 times minus 684. And then the 2 minuses become a plus. So really, this would be minus 20 times minus 684. But then the 2 minuses become a plus. I just don't have that much space to write here. That's why I skipped that step. But it's again, it's a minus and a minus together becoming a plus over here.
Okay.
Okay, you're welcome. Okay. So let's just finish the problem. So in this case, the length turned out to be 35, and the width was 12. So it's 2 times 35 plus 2 times 12. And so this comes out to be 94, which is exactly right. Okay. So yeah, so you have to set up the Pythagorean theorem, which gives you a complicated quadratic equation, which you then solve. And once you've solved that, then you know what the lengths of all the sides are. And once you know what the lengths of all the sides are, then you can figure out the perimeter. So it's a multi-step problem. Okay. And yeah, sorry, because I didn't have that much space to write, I had to skip a couple of steps in the algebra. But if you're doing it carefully, you'd write out that this is really 9 minus 4 times 5 times minus 684. And then when you simplify that, that's the same as 9 plus 20 times 684. And that's what's going to get you a solution. All right, any questions on this?
It's well understood to me.
Okay, good. Okay, so let's go to the next problem. So find the area of a rhombus with sides of length 13 and one diagonal of length 24. So this is going to be another similar problem. So we have 13, 13, 13, 13, and this diagonal here has length 24. We want to go find its area, right? And so if you recall, we have two formulas for area. So recall that we have this formula for the area of a rhombus. We did this last time, that this is equal to 1/2 times product of diagonal 1 times diagonal 2. Okay, so this is a formula for the area for a rhombus that we did last time. So we have diagonal 1, right? So all we have to do here is find diagonal 2. And maybe just for time, I'm just going to go ahead and do this because this is very similar to the first problem that we had, right? So the whole thing is 24, which means that half the diagonal here is going to be equal to 12. And so if we want to find x here, we can use the Pythagorean theorem. We'll again solve for x, and that's going to be the equation x squared plus 12 squared equals 13 squared. And that's x squared plus 144 equals 169. And that gives us that x squared is equal to 25, subtracting 144 from each side. And that gives us that x is equal to 5, exactly. So we have here that x is equal to 5. So that means if x is equal to 5, so that means the other diagonal. So the other diagonal is going to be 2 times 5, which is going to be 10, exactly. And so that means that the area, we have our formula, is 1/2 times 10, which is one diagonal, times 24, which is the other diagonal. And this comes out to be 120. Okay. So this is a rhombus problem. It's a lot like our first problem. What I should write down here, what I didn't, is that these rhombus diagonals also, they always make right angles. That's something special about a rhombus. That's not true about a parallelogram, and that's not true about a general quadrilateral. It's only something that's true about a rhombus, which is that the diagonals always meet at right angles in a rhombus. Okay. All right, so I wanted to do that one quickly because I do want to spend a little time on the next problem, which is a little bit more interesting. So any questions about this problem?
I think we move ahead, sir.
Yes. Yes, Prince? That's okay?
I think we can move ahead.
Okay, move ahead. Okay,
Yes, it's
great.
okay. It's
Okay, let's move ahead. Okay, so exercise 4 was this nice challenge. So it's find the area of the following trapezoid. Let me draw this a little better. So I drew the following trapezoid. Okay, so this is the following trapezoid, and here's how I labeled it. So this was 13, this was 15. Here we have a height with a right angle, and I said that this here was 5. And then also this side has length 20. Okay, so this is a multi-step problem, but what I want to just recall is the formula that the area is equal to the height times the average of the bases. So B1 plus B2 over 2, where this h is equal to the height, and B1 and B2 are bases, which is also, that's the parallel sides. Okay. And so if we want to find the area, we need to find these 3 numbers, right? We got to find these 3 numbers. And in particular, we found one of the numbers, right? So we know You can call this B1 is this top side that's equal to 15. So if we want to find the area, we need to be able to find the height, which is actually given by this length over here, h. And then we need to find B2, which is going to be the length of the entire bottom sides of the trapezoid. Yeah, when we derived this, we did this using areas of triangles. Yeah, so that's how we derived this last time. But for this time, we just have the formula.
So Dada Obus, can we say the height? Can we say the height equal to 12?
Yep, exactly. Great. So this height is equal to 12, right? So that's exactly right. And this we saw already, that with a right triangle, when you have hypotenuse 13, if one of the sides is 5, then the other side is 12. Okay, so ditto when one is 12, the other side is 5. So I'm going to just say, exercise height equals 12. What you're really doing is you're solving the equation, again, for a right-angled triangle, 5 squared plus h squared equals 13 squared. Okay, but in the interest of time, I'm not going to do it. I'm just going to say that h is equal to 12. So now the real question is, what is B2? Okay, so we need to find the length of this side at the bottom of the trapezoid. So any ideas on how to do this?
Okay, that over.
Yes, Abraham?
Yeah, let's say from the corner, the angle between 5, let me say 15 and 20.
Yep.
We draw a line there to hit B2.
Okay, great.
15 and 20, the angle are there. Okay, then we have right angle there.
Exactly, so now, great.
That line will also be equal to 12. That is the height.
That's great.
Okay, then we use a Pythagorean theorem to find the adjacent side.
That's great. So we have 12 squared plus x squared equals 20. And that's going to give us 144 plus x squared equals, 20 squared. Yes, yes, Princeton?
Can we say 16?
Yep, it's going to be 16, exactly. So this gives us x squared equals 256. And just to save space, this is x equals 16. Great. So this tells us that we have 16 over here. So this side over here is 5, or this part is 5, this part is 16. How much is this part?
So we have 15 in between it.
Exactly, 15 here, because this is just a rectangle. Everything here is a right angle. Good. So that means that the second base is just 5 plus 15 plus 16. So this is not drawn so well to scale, right? I really should have made this 20 side much longer, but it is what it is. So base is 5 plus 15 plus 16, which is 36. And so the area is 12 times 15 plus 36 divided by 2, which is 6 times 15 plus 36. And this comes out to be 306. All right, great. That's a perfect solution, Abraham. Okay, so yeah, so this is a little tricky because you have to really fill in the diagram with a lot more information than what's given to you at first. But you just have to realize what's the strategy here. If you weren't able to do this, you know that you need 3 quantities. And you can figure them out by using the Pythagorean theorem. Sorry, 1 second. So you can figure them out using the Pythagorean theorem, and you get h equals 12. And then once you have that, you can use the Pythagorean theorem again to get 16 over here. And then you can fill in the 15. And that's what's going to give you B2. Okay, yes, question. Did somebody just ask a question?
Yeah, hello. I'm not connected. Hello.
Oh, hi, Theophilus.
Hello, Theophilus.
Yes, hello.
Yeah, you getting me?
I'm getting you, yeah.
Okay. I was muted, really.
Yeah, you were muted.
Okay. I'm okay now.
Okay, good.
Yeah.
Good. Okay, so let's go on to a little bit of new material. I know we took a lot of time to do these problems, but I think it's important to go over them, especially some of the multi-step ones like this. Okay, great. So, okay, so I want to talk about regular polygons. So we mentioned last time that a polygon is regular. This means that all of its sides are equal and all of its angles are equal. That's what makes it a regular polygon. And we proved earlier, not just for a regular polygon, but actually for any polygon, that if a polygon has n sides, then its total interior angle measure is 180 times n minus 2 degrees. And that means that since you've got n different angles and they're all equal, that means that each interior angle is going to measure 180 times n minus 2, that's the total angle measure, divided by n degrees. So I gave a certain proof. Let me just give you an alternate picture for this. Let's say, n equals 6, just as a example. So what I did was I divided this all into triangles by drawing a point in the center and dividing it into a bunch of triangles. But you can also just pick a corner and draw all the diagonals that come from that corner. And so what we see is that this divides the hexagon into 4 triangles. Right, divides the hexagon into 4 triangles. Each of them has 180 degrees because a triangle has 180 degrees. So total angle measure is...
Hello, Dr.
Yes,
Dr.
hello.
Andrew?
Yes.
Dr. Andrew, Theophilus.
Yes, hi, Theophilus.
On the platform, but this is my first time to have this class, really.
Yes.
Yeah, I'm just starting for today, really.
Okay, welcome.
I need patience, really, please.
Okay, sure. But I mean, this, yes, that's fine. But I mean, also, like, the class is ongoing. I have to kind of assume the background from the earlier classes.
I'll pick up.
Okay, thanks. So we get 720 degrees, exactly. Emmanuel, you're trying to ask a question. Do you need to unmute yourself? Yeah, you've been muted on Zoom, so I can't hear your questions. If you unmute yourself, you can ask a question, but I don't know how to do it I can't do it on my end. You have to be able to do it. So what we see is this is 4 triangles. And how do we, and this reasoning, I did an example for n equals 6, but you can do this for any n. If I had a polygon with, 12 sides and I drew all the diagonals from one side, how many triangles do you get? Well, look at the far sides of the triangle from this point. It's this side, this side, this side, and this side. So it's basically every side of the polygon except for the 2 sides that are right next to the point, right? Except for the 2 sides that are right next to the point, the other sides are all the far side of one of the triangles. So that's an argument telling you that if you have n sides in your polygon, then the number of triangles you're going to get from this process is always n minus 2, because you get 1 for each side of the polygon except for the 2 that are right next to the point. So you're always going to get n minus 2 triangles. Each one will always have 180 degrees. And so this is another example. So this is another justification that the total angles of a polygon with n sides are going to be 180 times n minus 2 degrees. Okay. So yeah, so that's I drew the picture with n equals 6, but this is another justification in general for why this is true. Okay. And just a little table, just names of some polygons. We have triangle, quadrilateral, pentagon, hexagon. 7 sides is called a heptagon. 8 sides we know is an octagon. 9 sides is called a nonagon. 10 sides is called a decagon. 12 sides is called a dodecagon. And 20 sides, which is very hard to draw, is called an icosagon. There are other names for other numbers of sides, but most people don't know them. And most people, like, I don't even really remember what a polygon with 11 sides is called. It's called like an undecagon or something like that, but it's not really common usage. Even icosagon is not really very common usage. but 12 for a dodecagon is a little bit standard, so I wanted to include that. So if you go to a Wikipedia article on polygons, you'll see like what is the naming principle for every polygon. So if you had a 37-sided polygon, what would you call that? But in reality, nobody uses the names once the number is bigger. So if you have an example, if you have a 147-sided polygon, you would just call it a 147-gon. Okay, I mean, there is some appropriate Greek prefix that you could use for that, but nobody knows it and nobody will know what you're talking about. So if you have a large polygon, you usually just use the number. You just say a 147-gon. But for these numbers, the words are sometimes used. All right. Any questions?
Yeah.
Yeah.
Hello.
Yes, Theophilus.
On this formula, the 180th n minus 2. Is there any formula you can use? Like if I say 90th 2n minus 4.
Yeah, that's the same. That will also work.
Okay.
Yeah. So, and in fact, if you were Euclid, that's what you would do, because Euclid would say the total number of angles is the total angle measure is 2n minus 4 right angles, because Euclid's unit of measurement was the right angle. He didn't use degrees. So he did everything in terms of this is a right angle or half a right angle or whatever. So Euclid would say 2n minus 4 right angles is the total sum of the measurements.
Okay.
Yeah, so it's good. It is doing it like that. It makes you like Euclid, so that's good. Other questions? Okay, so one thing that's very, so we move on, one thing that's important about these regular polygons is that every regular polygon has an inscribed circle and a circumscribed circle. So this is not true for any polygon at all. It is true for every triangle, but every regular polygon has an inscribed and a circumscribed circle. So let me just draw a picture. I'll draw it again with a hexagon, just for an example. So let me draw a regular hexagon. I'll try to draw a regular hexagon. So the inscribed circle is the circle that's going to be tangent to the hexagon at the midpoints of all of the sides. So the inscribed circle looks like this. This is my drawing. It's not a perfect circle, but that's the inscribed circle. Actually, let me draw this in a different color. So the inscribed circle looks like this. I'll draw it in red. Okay. So that's the inscribed circle. And then there's a circumscribed circle also, which I'll draw in green. And that's a circle that passes through all the corners, passes through all the vertices of the hexagon. So that's going to look more like this. Okay, I'll try to do a slightly better job drawing that. Let me just do a better job drawing that. So the inscribed circle, the circumscribed circle is going to go around. Okay, no, it's not perfect, but it's okay. All right, so we have our hexagon in blue, and then there's the inscribed circle, which lies inside the hexagon, which is in red. And there's this circumscribed circle that goes on the outside of the hexagon, and that's in green. Okay, and each of these has a radius, so I don't want to clutter. Maybe I'll clutter the diagram a little bit. So the radius of the inscribed circle, so if I take a point from the center of the hexagon and I go to the inscribed circle, that radius is usually by little r, and sometimes it's called the in radius, and sometimes it's also called this word apothegm, which is, I mean, not that common a word, but you'll sometimes see it. So this distance from the center of a polygon to the midpoint of a side, which is the same as the radius of the inscribed circle, that's generally called either the in radius or the apothegm. And then you can also look at the distance from the center of a hexagon to a vertex, to the corner. That's the radius of the circumscribed circle, so I'll draw them in green. And that's generally just called the circumradius. And that's given by capital R. Okay, so the radius of the circumscribed circle is the distance from the center of the polygon to any vertex, because that's what the circumscribed circle goes through. And the in radius, or the apothem, is the distance from the center to the midpoint of a side, because that's where the inscribed circle goes. And I prefer in radius and circumradius because the words tell you what it means. Whereas if you think of the word apothem, unless you're a Greek scholar, right, the word just kind of doesn't mean anything. So you have to think, does this mean the in radius or does this mean the circumradius? And I will forget that all the time. So I'd rather just use the words in radius and circumradius because the words themselves tell you what they mean. Okay, so I will not really use this word apothem, but it's worth recognizing in case you see it. I don't know if exams sometimes use this word apothem, so it's good to know it if you have to recognize it. Okay, so any questions about this picture here? Let me just label the diagram. So green equals circle and red equals the in circle. Yeah, so the circles themselves are sometimes called the circumcircle or the incircle. That's just shorthand for a circumscribed circle and the inscribed circle. Okay, so these polygons have these circles. And so let's say that we wanted to find a formula for the area of a regular polygon. So let's say we have a regular polygon with n sides. So we have a bunch of different data that has to go in. So let's say that we have n sides and each one has side length s. And let's say that the in radius of the polygon is r, little r, and the circumradius of the polygon is big R. So if we want an area formula for the regular polygon, we're going to calculate it by dividing it into triangles. So I'm going to draw a diagram. I want to draw it a little bigger, and it's going to look like this. I'm not going to specify how many sides this polygon has. I'm just going to draw kind of two vertices here. And then, it's just assumed that this polygon goes on. But I don't need to really specify how many sides. So these are all sides, and each side has length s, right? So they all have length s. And then here's my center, right? And so in particular, I can draw a right. So remember, the only shapes we really know how to calculate areas of are triangles and quadrilaterals. So, and at that, only special quadrilaterals. So if we want to determine the area of a more complicated shape, the best way to do that is usually to divide it into triangles. Okay? So what I'm going to do is I'm going to draw this triangle over here. Okay, so I have my center. This is the center of the polygon. And I'm going to draw the line from the center to the midpoint of the side. So that's going to make a right angle because it's exactly bisecting the side. And what do I know about this? Well, this is the in radius, right? This length from the center to the midpoint of the side is the in radius. That's little r. And this length over here from the center to a vertex, that's the circumradius. That's r. Okay? And this here, maybe let me just erase. Wait, no. Yeah. So instead, I'm going to write the s up here, but here we have 1/2 s. Well, I'll just write s over 2. Here we have s over 2, and here we have s over 2. Right. Okay.
Yeah.
So
yeah.
What's the area of what's the area of the triangle? So what's the area of the triangle here?
So we call the formula for x A is equal to 1/2 b times h, which is the area of the triangle.
Exactly. So in this case, in terms of r and s, what would we get if we want it? Right. So the area of a triangle is 1/2 base times height, which in this case is what?
Yeah, so we have half multiplied by r.
Yep.
Multiplied by s over 2.
Exactly.
That if we cancel off.
Yeah.
I mean,
Right. Exactly. So this becomes RS over 4.
Yes.
Right. Okay. So this area of triangle is RS over 4. Now here's the question. So how many triangles like this make up the polygon? So how many of these triangles do I have to put together to make the whole polygon, right? I mean, I can put another one here, and then another one here for the next side, and another one here, and so on, right? And so on. So if I want to make the whole polygon up of these triangles, how many of them, and remember, the polygon has n sides. So how many triangles do I need like this to cover the entire polygon?
Let me try some.
Yes, Prince?
Yeah, 4. Can we say 4?
Well, I'm not telling you how many sides the polygon has, right? It just has n sides. N could be anything. So I drew 4 triangles here, but this polygon might have 100 sides for all we know, right? So the answer is not going to be a number. It's going to have to be in terms of n. So if I've got n sides.
Yeah. So,
Yeah.
so we have, since we have one of the sides divided into two triangles, right?
Yep.
So we have so if we want to know, I mean, and want to calculate the total number of sides, or how many sides we have over there.
Yeah, so the number of sides is n. Yeah.
I think it'll be n.
Right, so the number of sides is n. Not n divided by 2, right? And we have 2 triangles for each side, right? So we've got n sides and 2 triangles for each side. So the total number of triangles is
16.
Well, it's not going to be a number, right? Because it's going to depend on n. It's going to be an expression in n. Right? So we got 2n, exactly. Yep, 2n, right? Because we have n sides and each side gets 2 triangles, right? So if we had 8 sides, we would have 16 triangles, right? And if we had 100 sides, we would have 200 triangles. And if we had 4 sides, we would get 8 triangles, right? So it's always going to be 2 times the number of sides because we have 2n, we have 2 triangles for each side. So the total triangles is going to be 2 times the number of sides, right? So the answer is 2n, is 2n of these triangles. Is that okay? Is that clear?
That's right, it's clear.
Okay. So that means that the total area is what? Well, we have each triangle, well, there's 2n triangles, and each triangle has area RS over 4, right? This here is the number of triangles, and this here is the area of each triangle. So it's 2n times RS over 4, and if we simplify this, this becomes nRS divided by 2. So this is the formula for the area of a regular polygon. Okay, this is a formula for the area of a regular polygon. So it's equal to nRS over 2, where n is the number of sides, s is the length of each side, and r is this in radius. So in this formula, actually, we don't need to use capital R. It doesn't show up at all. And so it's the product of the number of sides, the length of each side, and the in radius. So this is a formula for the area of a regular polygon. Okay. Now what we're going to do, the last thing we're going to do today is we're going to try to get a formula that involves only n and s. Okay, so we don't want to use this r maybe, because if I say, hey, you have a hexagon and each side has length 5, what's its area? Then I haven't told you the in radius. So it's probably better to just get a formula that involves only n and s. So this is going to be our first formula, but we're going to get a better formula on the next page, which uses only the length of a side and the number of sides. Okay, so but before I do that, are there any questions on how we did this? The goal is to find the area of each triangle and then realize that there's 2n of them. and then you multiply them all together, and that gives you the area of the whole polygon.
So the obvious.
Yes.
Hello.
Yes, hello? Theophilus?
Yeah, hello.
Hello, yes.
So yeah,
Princeton.
in the total, yeah, so that means the total area of the polygon. So that means the total area of the polygon formula is NRS over 2.
Yep. Yep. NRS over 2,
Okay,
but
okay.
you have to know what N, R, and S all mean, right? N is the number of sides, S is the length of each side, and R is the in radius.
Well, yes, sir. If for instance
Yes,
I'm asked
Prince.
to find just to find the area of the polygon, it would be RS over 4.
No, that's the area of one of these triangles is RS over 4. Right?
Okay.
So it's the area of a triangle. So if I draw one of these right triangles, it has area RS over 4. The whole polygon is 2n of these triangles put together. So you have to multiply by 2n, and that's why you get this final formula.
Okay. It's well understood.
Okay, good. Other questions?
Yeah, hello?
Hello, yes. Theophilus?
Yeah, I want to know the difference and the function of this small arrow and the big arrow.
So in the area formula, the big R doesn't figure in. We don't use it at all. It's just, the point is, if you have a circle, we haven't really talked about circles, but circles have a radius, right? You can go from the center to the outside of the circle. That length is the radius. And it doesn't matter what point you go to. They're all the same radius. But for a polygon, let me go back to this page. For something like a hexagon, what is the radius of a hexagon? The answer is, well, you don't know, because just saying the radius doesn't tell you enough, right? The radius could mean that I go from the center to the middle of a side, or it could mean that I go from a center all the way to a vertex. And so the small r is like the smaller radius. That's what you get when you go from the center to the middle of a side. And the big R is the big radius. That's what happens when you go from the center all the way to a vertex. That's going to be a longer distance than going from the center to the middle of a side. Okay, so that's the, and either of these could really be called the radius, right? And so the point is, when we're talking about polygons, we don't use the word radius because we have to be more specific than that. So we have the in radius, which is the little r, that's the smaller radius, and we have the circumradius, which is the big R, that's the bigger radius. So that's the role of both of them. Either one of them can be the radius, depending on, you know, what you want to know about the polygon.
Okay.
Okay.
Thank you.
You're welcome. Other questions? Okay, so let me do, so this last slide, I'm going to apologize. I've tried to avoid trigonometry during this unit on geometry, but for the next slide, we're going to have to do a little bit of trigonometry. So if the trigonometry makes sense, then that will be helpful. So what if we want the area formula in terms of only S and N? So sorry, that L should be an S. So let's say that we want the area formula. Here we have this nice formula, NRS over 2, but maybe we don't want R, right? Maybe we want to just use the side length and the number of sides. So I say I have an octagon and each side has length 10. What's its area? So what we need to do is find a formula for R in terms of S. And if we can find a formula for R in terms of S and N, then you know, we're good. Okay, then we can write everything in terms of S and N. Sorry, question?
Then we can substitute that.
Yeah, we'll do a substitute, but we have to use a little trigonometry to make that work. So let's write this. So the goal, you know, express, yeah, and correct. Once we have this formula, then we can just substitute it in for R over here. We can just substitute it in for R. So the goal is express r in terms of s and n. And since we only have 10 or 15 minutes, let me just show how we're going to do that. Well, if I look at this same right triangle that we had before, right? This was r, this was s over 2, and this angle here we're going to call theta. But remember, is that two n triangles make the polygon. So in fact, theta is just equal to 360 degrees. That would be the full circle if we put all of these triangles together, and there's 2n of them. So theta is just 360 degrees divided by 2n. Okay, or in other words, 180 degrees divided by n. Okay. So theta here is what is this angle? It's actually 360 degrees, which would be the full circle, but it's cut out into 2n pieces. So each one of them is just 360 degrees divided by 2n. Okay, or 180 degrees divided by n. And so now here's where you need to use a little bit of trigonometry. We have that the tangent of theta is the opposite side over the adjacent side. So the tangent of theta is s over 2 divided by r. And so now if we want to, or tangent of 180 degrees over n is equal to s divided by 2 over r. And so now if we want to express r in terms of s and n, this yields that r is equal to s divided by 2 divided by the tangent of 180 degrees over n. Okay, just by multiplying r to this side and bringing the tangent down to the other side. Or if we want to just write it as a simple fraction, r is equal to s divided by 2 times the tangent of 180 degrees over n. Okay, so this is how we get r in terms of s and theta. You have to use a little bit of trigonometry, remembering this is a right triangle, so you have to use tangent of theta in order to get the ratio between the r and the s over here. So now what this tells us is that the area, which we have our formula from before, this is nrs over 2, but now instead of r, we can use this formula instead. We substitute in. So this is the same thing as ns over 2 times s divided by 2 tangent of 180 degrees over n. Or in other words, this is going to be ns squared divided by 4 times the tangent of 180 degrees over n. So it's maybe not as nice a formula because it involves trigonometry. It involves these tangents. But it is nice because it doesn't involve the in radius at all, right? It just involves this number of sides and the length of each side. So this is a formula that's purely in terms of n and s. So if I say, what's the area of an octagon with side length 4, then you can just plug in n equals 8 and s equals 4 to this formula, and it will give you the area. Okay, you don't have to figure out the in radius or figure out, do a diagram drawing this into triangles or anything like that. Okay, so just to recall what we did here, we wanted to get r in terms of s and n. So we make this right triangle. We know the angle here is 2n of these angles makes a full circle. So this angle is 360 degrees over 2n, or 180 degrees over n. And then using trigonometry, we know that the tangent of this angle is s over 2 divided by r. Okay? And using all that, we can use algebra to solve for r in terms of s and n. And then I'll just write this, we substitute for r. And if we substitute for r, we get exactly, instead of nrs over 2, which is the formula we had from the previous page, now we get ns over 2 times this thing that we substituted for r, right? This whole thing here is r. And then when you do it all together, you end up getting this formula. So ns squared divided by 4 times the tangent of 180 over n. Okay. Questions on this? We'll do the examples of a triangle and a square on the next page, and that'll be the last thing we do today. But before we go on to the examples, any questions? It's a bit of a, it's a serious derivation. Okay, if no questions, let's just do an example. Okay, so we've seen on the previous slide, I don't mean L, I mean S here, that the area of a regular polygon with n sides of length s is given by this formula, ns squared divided by 4 times the tangent of 180 degrees over n. Let's calculate this for 2 nice familiar cases. This is a triangle, and this is a square. Right, and this is not just any triangle, but this is an equilateral triangle, right? Because it's a regular polygon. So let's look what happens here. So if we have n equals 3, we get that the area of this triangle with SSS as the length of the sides, this is equal to 3 times s squared divided by 4 times the tangent of 180 divided by 180 degrees divided by 3. So that's 3s squared divided by 4 times the tangent of 60 degrees. Anyone remember what the tangent of 60 degrees is? I know we haven't been doing any trig, so this is if you just remember what tangent of 60 degrees is.
Root 2, root 3 root 3.
Yeah, root 3 over 3, exactly. Great. Oh, no, sorry, it's just root 3.
Okay.
It's just root 3. Yeah, so that's 3s squared divided by 4 times root 3. Yeah, you got to go back to your trig tables and see these. But yeah, it's 3s squared divided by 4 times root 3. And this simplifies. 3 divided by root 3 is just root 3. So this simplifies to square root of 3 over 4 times s squared. And maybe you've seen this before. This is the formula for the area of an equilateral triangle with side length s. Okay, it's square root of 3 over 4 times s squared. Okay, so that's what happens when n equals 3. What about when n equals 4? This is the area of, well, this is the square with side length s. You already know what the area of this is. It should be s squared. So let's make sure our formula works. Let's make sure we're not getting a bad answer. Well, I'm going to substitute, just like what James said in the comments, I'm going to substitute n equals 4 here. So that's going to be equal to 4s squared divided by 4 times the tangent of 180 degrees over 4. Well, the 4's cancel out. So I get that this is s squared divided by the tangent of 180 degrees over 4 is 45 degrees. Anybody remember what the tangent of 45 degrees is?
Tangent 45 degrees is equal to 1.
Yes.
Is equal to 1. Exactly.
It's
It's 1. Exactly. The tangent of 45 degrees is 1. Exactly. So that's s squared over 1, and that's s squared, which is very good because it should be s squared, right? Whatever this formula is, this is supposed to be some general formula that works for any n. It better work for n equals 4, right? N equals 4 is going to give you the area of a regular polygon with 4 sides. That's a square with length s. So we know the area of a square is s squared, and this shows that this complicated formula, when we plug in n equals 4, it actually simplifies a lot down to s squared. Okay? So So yeah, so Emmanuel, by the way, there's no we're not getting your Zoom is on mute this whole time. We haven't gotten any I haven't been able to hear any questions or anything. I saw that you wrote in the chat, but you have to unmute your Zoom in order for us to hear your questions, and I can't hear anything. Okay, so for an equilateral triangle, we get √3/4 times s squared. For a square, we just get s squared. And as we have more and more sides, we're going to always have an s squared, but we're going to get some different coefficient, which is going to be n/4 times tangent of 180 degrees over n. Okay. Questions? Yes. Okay.
Yes. For the you got 3, which is the triangle.
Yeah.
We have 3s squared or 4 times the √3. But in the formula that you circle there, you get only √3 or 4 times s squared. So where the 3 are top the s squared, what is it now?
This is because 3 divided by square root of 3 is equal to square root of 3. So, right, because square root of 3 times square root of 3 equals 3. So 3 divided by square root of 3 is equal, I mean, you know, if I wanted to derive this, I could write that 3 over square root of 3 is equal to 3 square root of 3 over square root of 3 times square root of 3, right? And multiply by √3 over √3. This is 3 square root of 3 over 3, and this is square root of 3, right? So what I'm doing is I'm taking the 3 and dividing by the square root of 3, and what I'm left with is just a square root of 3 on top.
It just simply means a rationalize square root.
Exactly. I'm just rationalizing the square root to make it simpler. But I mean, if you wanted to leave the formula like this is fine. This is correct. But this is just a simpler form. Right, 3 divided by square root of 3, it's just simpler to write it as square root of 3 in the numerator with nothing in the denominator. Okay. Good. Other questions?
Hello?
Yes, Abraham.
I'm really getting confused for where you get, let's calculate this in case n is equal to 3 and n is also equal to 4.
Right. I mean, so you can do any n, right? So the n is telling you the number of sides of the polygon, right? So if I plug in n equals 3, that's giving me the area of a triangle. If I plug in n equals 4, that's going to give me the area of a square. If I plug in n equals 5, that will give me the area of a pentagon. So this one formula works for every different shape, but you have to choose the right number of sides, and you get the area of that shape.
Okay, thank you. That is 2 different problems.
Yeah, exactly. It's 2 different problems. That's why we get 2 different answers, right? The triangle is square root of 3/4 times s squared, and the square is just s squared.
Okay, thank you.
Okay, you're welcome. Other questions?
Yes, sir.
Yes.
Yeah, to me, what I want to say is that the n stands for any number of polygons that is given. So if it was going to be n equal to 9, then you look at the type of polygon, right?
Exactly. So that would give you a nonagon with each side of length s. If you plug in n equals 9, that will give you the area.
Okay.
Yeah. And so maybe the homework will make this clearer, actually. So the homework problem is to calculate this for a hexagon. So the regular hexagon has side length s. So what is its area? So that this problem is just asking you to just plug in n equals 6 to the formula over here and see what you get, because it's a hexagon. So the regular hexagon is side length s. What's its area? So you're going to get an answer here. And then question number 2 is compare your answer to the area of an equilateral triangle with side length s, right? This we already figured out. This equilateral triangle with side length s we saw as square root of 3/4 times s squared. So the question is, how many times bigger is the hexagon's area than the equilateral triangle's area? And then the question is, can you find a geometric reason? So you're going to get that the hexagon has area like some number of times bigger than the triangle. And then the question is, can you give a geometric reason why this should be true? Okay, so it's a bit of an open-ended question. But part 1 is a straightforward question. You just want to plug in n equals 6 to the formula and see what you get. And then part 2 is to basically compare what you get for n equals 6 with what you get for n equals 3. and see like how much bigger is the n equals 6 than the n equals 3? And then is there a reason not using the formula that you can like tell that you should get this ratio between the two things? Okay. So, all right. So that's the day. So thank you for your attention as always. Please remember to type your name into the chat if you have not typed it in so far. So please type your name for attendance. Attendance, I think I spelled it wrong. And there will be no class next week because I'm going to be at a conference. But on January 19th, we'll continue and we'll move on from polygons to circles. So we'll start talking about circles. We'll start talking about circles next week, next time. Okay, so I'll remind everybody that there's no class next week. All right, any questions on anything from today?
Thank you, Dr. Robert.
Okay, you're welcome.
Yeah,
Thank you, Andrew.
Yes, you're welcome, Sange.
Yeah, Andrew.
Yes, Charles.
Yeah,
Oh, sorry, Abraham. Yes.
Yeah, thank you very much for the class today. I hope on the 19th we'll be able to come back into class. Thank you very much.
Yes, definitely. Thanks, Abraham. Okay. Any other questions? So, as usual, I'll post the notes in the chat room and I'll post the video on YouTube. Okay. Anybody else want to write their name into the chat before I close out the room? Or even write anything into the chat. I just need a record of you having been. Let me actually just type some names of people who haven't written this in. So Bissy, Ade, Allison. I'm just going to type some names so that I have the record in the chat. Bissy, Ade, Allison. Let's try. Okay, maybe that's. Okay, and I think everybody else has written their name in at some point. Okay. Did I get? Oh no! He wrote already. Okay. Great. Okay. All right. Well, then have a great weekend, everybody, and I will see you in 2 weeks.
Thank you.
Thank you.
You're welcome. Happy New Year, everyone.
Happy New Year.
Thank you, God.
Bye-bye.
All right. You're welcome. Bye. Bye, everyone.